Okay, in this video we're taking a look at scale factors. So on the top left here I have two little people who are clones of each other, and in math if objects are exactly the same size and shape we call them congruent, and this here is the symbol for congruent. If they're not congruent they might be either reductions or enlargements. So it's the same shape, but they're not the same size. They're called similar images. If you reduce something and get a little guy who's smaller, it's called a reduction. And if you enlarge it, it's called an enlargement. And you can do this not only with little people, but you can also do this with geometry objects. So I've got two triangles here that are similar. One triangle is called A, B, and C, and I denote that as triangle ABC over here, and the other triangle is called D, E, and F, and I've denoted that as triangle DEF over here, and this little symbol in the middle is so that I don't have to keep writing out similar. It's the kind of equivalent to the congruency symbol, which means exactly the same size. This is whenever you have reductions and enlargements. Similar figures use that little squiggle. Now, the order of importance is very, very key to these similar statements. So A to B on this graph, this side here, is the one that's similar to D to E on this picture here. So you have to be very careful with your lettering so that the ones on this one line up or match up with the ones on the other one. Now, this idea of things being either congruent or bigger than or smaller than leads us into something called a scale factor. If the scale factor is 1, the images are exactly the same size and shape, they are congruent. If the scale factor is smaller than 1, you're dealing with some sort of a reduction, and if the scale factor is larger than 1, you're dealing with an enlargement. So let's take a look at that next. So the scale factor is a comparison of, or scale factor equals, the image length compared to the original object length. So if the original object and the image are exactly the same lengths, heights, widths, then those will both be the same, and it'll be 1 and 1 or 10 and 10, and it'll equal 1, and you'll have congruent objects. If the scale factor of the image compared to the original is smaller than 1, it's a reduction, and larger than 1 is an enlargement. So if I take this example which is in red, and I start off with a triangle ABC, and it's similar, so I've written down here, it's similar to triangle DEF, and I have some numbers, 4, 2, and 5. Don't worry that they're not to scale, they're correct. The math is right. And this other object maybe isn't a perfect enlargement or reduction. This looks like an enlargement. So this is the original. This is the new one, which we call an image. And now I start looking for comparisons. So A to B on this side is 4, and A to B on this side is 8. And I'll pretend we don't know these numbers here quite yet. But 4 compared to 8, 4 goes on the bottom, that's the original object, and 8 is the image length, that's DE, and that's a scale factor of 2, which means to go from here to here, I'm doubling, I'm multiplying things by 2. And so to go from BC, which lines up with E to F, you're doubling. So 5 doubled becomes 10, and on the bottom AC matches up with DF, that becomes doubled, which is 4. Now, the scale factors aren't always this easy, so in the next example we're going to take a look at what happens if the numbers are a little bit more complicated. Okay, so in this example I've got a couple of triangles, ABC and DEF, and notice I've spun the triangles around a little bit, but they're still similar to each other. So we just need to figure out which sides match up with which sides, and a scale factor doesn't matter which lengths we use, so I could use this A to B, and I know it's got to match up with this D to E, and the D to E goes on the top, so DE, and the AB goes on the bottom, so this will be the original and this is the new image. Then I can compare BC to EF on this picture. So EF goes on the top and BC goes on the bottom. And that would be the same comparison as the final two sides, which are AC and DF being compared. Now I can start to fill these things in. So AB I know, that's 13. DE I don't know, but I called it the letter Y. EF is X, and BC, which corresponds to it, is 12. DF is 10, and A to C is 7. And you can actually see that your scale factor is 10 over 7. So it's enlarging, but it's not enlarging by a nice easy number. So when I do these calculations, there's a neat little trick you can do, which is just work with a bit of this at a time. So if you take these two pieces of information, you can solve this. All you need to do is multiply both sides by 12, and you'll get x equals 120 over 7, which isn't a very nice number in terms of being an integer, but it is a number, and it is actually the length of side x. And I can do a similar thing by taking these two numbers, so 10 over 7 and y over 13, and just saying, okay, well, y over 13 is equal to 10 over 7, and again, just solve by multiplying by 13, and I get y is equal to 130 divided by 7, and I have my two side lengths, and I have calculated some things about these triangles that are similar. Let's take a look at what happens if we do this on a Cartesian plane or on a grid. Okay, so we're going to start off with an object. I'll just make it a little tiny square right here, and I'll call it A, B, C, D. And what I want to do is increase this by a scale factor of 3. And whenever I do that in a grid, I'm doing it from a point. And generally the point is the center, so from 0, 0. And the way that I do that is I measure how far away these points are, and I triple that distance because of scale factor 3. So I kind of go diagonally up to A, and I think, okay, this shape here, like 1 over and 2 up, gets tripled. So 1 over and 2 up would go here, and another 1 over and 2 up would go here. And this is where my new A value will be, and we generally call that A with a little line, or A prime. If I do B, B's like diagonally across 1, and now I go diagonally across 3, and I end up with B prime. C is 2 over and 1 up, so I go 2 and 1 again, and 2 and 1 again. I end up with C prime. D is 2 units, and then 2 units, and 2 units, and I end up with D prime. And then I just play connect the dots, and I end up with a larger square. In fact, every side length is 3 times the original one. That's one way, and I find that the easiest way to do these constructions on a grid. There's another one where if you know where a point is, like A is 1, 2, look where A prime now is. It's 3 across and 6 up. And hopefully you can see what's happened to these coordinates relates to the scale factor. And the same thing happens with B. B was at 1, 1, and if you want to guess where it'll be, you'll be right. It'll be now at 3, 3, and the same thing happens with C to C prime and D to D prime. Okay. There's also some interesting things that happen with the area. Notice the area of the original one is 1 square, but now the area of the new one certainly isn't 3. It's much bigger than that. So there are some quirky things that will happen with some of these questions that you'll get asked during the homework as well. So just be careful with that. Okay, we'll see you in class.